see, right? Yeah.
Yes.
So, good morning. So, yesterday we looked at the molecular basis of signaling in a neuron. We saw that there are four signaling components in a neuron. Right? If you look at a simple toy model of a neuron, see, okay. So you have dendrites, right? Some cell body, soma, then axon. Axon branches out into axon collaterals. At this point, you have a synapse. Axon, soma, and dendrites. So we talked about the signaling components in all these four regions of the neuron. Right, different things happen in different places, different kinds of propagation occur in different places. And one of the most important events is the generation of action potential. That is, if you inject current into the neuron, so you give a current pulse, then that if the current pulse is of sufficient amplitude, it generates action potentials which propagate down the axon. So now we want to describe this mathematically. So we won't be describing the whole neuron and all this detailed processing right away. We look at only one essential part of it, most important part of it, which is generation of action potentials. So for that, we assume what is called, we make what is called isopotential assumption. So instead of modeling this whole complicated neuron with very complex geometry, we'll imagine that there is just a sheet of membrane, right, and potential is uniform right across the sheet. And inside this sheet, there are some ion channels and all that. Now, so this is outside and this is inside. Now we inject some current into this sheet by poking it with an electrode. So inject some current, Ix. Okay, so now as a function of this, in response to this injected current, how does the voltage is inside, right? Vm. How does the voltage change? This is what we'll be looking at. You can think of it as a sheet, or you can think of it as a sphere, whatever it is. The voltage is uniform, right? It's homogeneous. Potential is same everywhere. So let us look at this, because if you understand this, we can elaborate this and then study how signal propagates from one point to another. So in this assumption, since the voltage is same everywhere, there is no space variable. Because if you look at the real neuron, which is an extended body, right, extended through space, the voltage varies from point to point, also from with time. So voltage here is actually a function of both space and time. Space here is actually, if you look at neuron, it's a three-dimensional object. So it will vary with position in three-dimensional space. But we'll look at only a simple situation now. We'll make a supposition assumption and assume there is no space. We're looking at like a point or a small region where the voltage is uniform. Now, how does voltage vary with time alone? No space variation. Okay, so this part of the bigger problem is what we will study now, and this is what was worked out by Hodgkin and Huxley. In Hodgkin and Huxley, they didn't actually look at a sheet. They didn't look at a sphere also. What they considered is a cable, a cylinder, right? In a cylinder, here also the isopotential assumption is valid, is made valid, but that is, they made sure that the potential along the cable is uniform. And here they injected some current into it and then measured the voltage, that is voltage inside the cable, Vm of t. So in all these cases, whether you imagine as a sheet or a sphere or a cable or a cylinder, right? What is common to all these things is you assume that there is no variation with space, right? Voltage is uniform, and then if I inject some current, what is the response? So this is called the Hodgkin-Huxley model. So just to repeat from yesterday, so neuron, you can think of it as a ball or some object which has a uniform potential inside in resting condition. And if I inject some current into it, there's a fluctuation, this voltage changes, it produces sharp fluctuations called action potentials. So we have seen all that. We have also seen that there are two kinds of channels, right? Voltage independent and voltage dependent. It's the voltage independent channels that we call the leakage channels. They're called leakage because since they are constantly open, right? They constantly leak charge or leak current. So therefore, they're called leakage channels. The voltage dependent channels can be opened or closed with the help of voltage by varying voltage. That's the sodium potassium channels we have seen yesterday. So we have also seen the Nernst potential, which is given by this formula, right? The ratio of concentration between two chambers gives you the voltage difference between the two chambers in the opposite direction. So you see that x2 by x1 determines v1 minus v2. So there is a note that difference in sign. And each channel can be represented as a series of a conductance and a battery, right? The channel conductance and the Nernst potential of the that you get from the Nernst potential equation. In case of voltage dependent channels, the conductance is varying, so it is denoted by this arrow. So for potassium, the Nernst potential is minus 77 millivolts, and the GK, the conductance, is 36 millisiemens per centimeter square. Like I said, we talk about conductance in terms of per unit area because we make this, all the channels are sit across the same membrane, across the same potential difference. So they are in parallel, and conductances add up in parallel. Right. So if you assume a large sheet, we don't have to study the entire sheet, but we look at only a unit area of the sheet. So the K plus equivalent circuit is like this. Similarly, the sodium data is like this. So the sodium ENA is given by this formula. You get 50 millivolts, and GNA is somewhat high, 120 millisiemens per centimeter square. So this is the equivalent circuit of sodium. Then the leakage channels, there are a whole bunch of them, and I mentioned yesterday that you can add up all of them, invoke the Thevenin's theorem, and just combine them all into one conductance and battery branch. So finally, you get an equivalent circuit like this. Okay. It's given by this. So thing is, one thing I want to point out here is in some of this biologically oriented literature, right? Textbooks written by biologists, the circuit is given in a slightly different fashion. You will see that the batteries change. Sometimes it is this way, sometimes other way, and so on. So what we'll do, I'm showing batteries all in the same direction, okay? Because ENA is actually positive, EK is negative. So in biology textbooks, they actually flip the terminals. What I'm doing is I keep the terminals the same, but numerically I use appropriate values. So ENA is plus here and minus here, and the ENA value is taken as plus 50 millivolts. EK is plus here and minus here, but EK value numerically is taken as minus 77 millivolts. So I take care of the sign by simply using the right numerical value. I don't flip the signs here in the picture because it looks very confusing. Okay, so current is injected here, and voltage is measured from inside to outside, right? And this is a capacitance. So now, if you apply the Kirchhoff's current law here at this node, then you see that the Ix is shown as going into the node. Okay, whereas the IK, the other currents, INA, IK, and all that, right, are shown going out of the node. They're in this direction. So if you apply the Kirchhoff's and even the IC, that is a capacitive current, is like this. So if you invoke the Kirchhoff's current law, Ix is given as IC plus INA plus IK plus IL, the leakage, right, the leakage currents. and these can be calculated like this. IC is, right, C dV by dt, then INA is Vm minus ENA times GNA. Okay, and similarly the IK, right, is GK times Vm minus EK. Similarly, IL is GL times Vm minus EL. This whole thing is equal to Ix. Okay, so this is the basic equation. This is the voltage equation, and we should remember this well because we'll be doing more of this later. Right? We need to learn how to write this equation. And note that there is no space variation here. There is a different ordinary differential equation. There is an ODE. Right? We are not talking about how voltage changes with space because there is no space here at all. Later on in the course, when we want to discuss how voltage wave propagates along the cable, that one will include space variation, and we'll use a partial differential equation where you also have space derivatives along with time derivatives. But in this case, there is no space variation, so there's only a time derivative. So you're talking about an ODE. Now, this equation obviously is not complete because the main thing which is missing in this equation is we know that GNA and GK are variable conductances, and in fact they are dependent on the voltage itself, right? Because they're voltage dependent channels. So Vm somehow controls GNA and also GK, right? How is the question? This is the most crucial question in the Hodgkin Huxley model. So let us see how it works out. Now, to understand that, right? So we said GN and GK they vary as a function of voltage, right? We said there is some voltage gating. Now, how exactly does this voltage gating work? How does the voltage of the membrane, right, the membrane voltage, control the conductance of a channel? Now we need to remember that these channels can open and close, and that's what is getting about. And there are 4 different mechanisms by which a channel can open and close. Now, so we need to understand this specific kind of voltage gating, channel gating, which is voltage gating. We need to find out how the voltage can switch this channel between closed and open states. So we'll look at a simple channel where the channel can only sit in 2 states, open and closed, because there are more complex channels which are thought to go through more states. So for example, right, you can have open is one state and close is another state. In a simple channel, they just go flip between these 2 states. So this is a simple channel. In more complex channels, people invoke or assume like a whole variety of states and call them S1, S2, etc., etc. Right, and it can go back and forth. And they're more complicated. You have whole graphs that describe the variation, the transition of the channel from one state to another. And open and close are only 2 states among many states. Okay, but in case of Hodgkin Huxley model, the way they describe the open close dynamics of sodium potassium channels, they assume a simple kind of a channel where it just switches between open and close. Okay, so let us assume a simple channel model for the sodium potassium, where the channel simply switches between 2 states, closed and open. Now, just as in a first order reaction, a chemical A becomes B and the chemical B, the reverse direction becomes A. And you know how to describe this, right? In using Arrhenius, the law of mass action and all that. So we'll use a similar principle to describe how the channel becomes switches between these 2 states. Right, that's similar to this transition bit of chemical A to chemical B and back. Now the forward reaction from closed channel to open channel is governed by a reaction constant K plus, and the reverse reaction from open to close is governed by another rate constant K minus. Right. So given this, we can describe the open close dynamics as a first order reaction, first order equation like this. Now consider X as a fraction of the channels in open state and therefore logically, since there are only two states, 1 minus x is a fraction of channels in the closed state. Now, if you also invoke this first order dynamics here and use these rate constants, right? Dx by dt is equal to so the open ones become closed, therefore thereby depleting the number of closed channels, right? So you have minus k minus times x. X is this. This is 1 minus x. And the closed channels become open, thereby enhancing or increasing the number of closed channels. Therefore, that is plus k plus times 1 minus x. So this is the basic equation that describes how the number of or the fraction of the open channels in open state or open channels varies with time. So here so you can do some simple algebra here. You group things around a little bit, regroup things is equal to take the terms which are dependent on x, right? You get this kind of a form. So now divide both sides by this term k plus k minus. Then you will have some factor times dx by dt minus k x plus x infinity, where tau is nothing but, right? So this goes to the left side, k plus k minus goes to the left side. It becomes 1 by k plus k minus. That is your tau, right? And not tau infinity, it's just tau. Whereas k plus by, so divide the whole equation by this, so you get k plus by k plus k minus. That is called x infinity. The whole idea, reason we are calling it x infinity is this is a value to which x tends, right? In its steady state, after infinite time, after a long time, x tends towards this quantity, therefore it is called x infinity. And the tending occurs over it because it's an exponential approach to x infinity. It will actually approach, let's say x starts from 0 and then x will rise in exponentially to this value. This is x infinity. And the time constant of this rise, right, that is given by tau. Okay, so that is how you describe the dynamics of the open-closed dynamics of the channel. Now note that when we are describing this kind of a dynamics, we are not describing the dynamics of a single channel, because single channel dynamics can be pretty complicated, right? With this only because the law of mass action is a statistical law. It says that if you look at a large number of molecules, right, where one becomes the another and so on, A to B, B to A and all that, then the concentration of the molecule of that chemical varies in this fashion. So the law of mass action is a statistical law. So similarly here, what we are describing is not the dynamics of a single channel, but of a whole population of channels. And just for information, a single channel, the way the conductance varies is actually pretty complicated. So people were able to measure the current going through a single channel. So this is the membrane, this is the channel. I'm looking at a section of a channel, so it's like a cylinder, right? And then there is current going through it, right? IT. This current is plotted in this graph. You see that it is going between two limits, 0 and some picoamperes, a very small current. So 10 power minus 12, right, amperes. So it just shows a very sharp spike of current, like a pulse of current, and then remains 0, and then a sharp pulse again remains 0. So basically what this graph tells us is that the channel opens completely, remains open for some time, allows current to pass, again closes rapidly, very rapid closure, right, remains closed for some time, no current, again opens and allows full passage of current for a brief time, and so on. So so the channel actually it just flutters, you can say, right? It shows us very rapid open close dynamics. So therefore, what we are describing here is not that kind of dynamics. What we're describing is the dynamics of a population of channels. So if you take a large number of these, which are present, right, in a few thousand of them present in a small patch of a membrane, like say a few hundred square microns, something like that. Then the current, right, in that membrane, which presents the total current flowing through all those channels, that will show a much smoother variation, which will look like this graph here. And this is a kind of dynamics that is being described by this equation. Okay, so we are not looking at single channel dynamics. Incidentally, this kind of a graph that shows the current through a single channel, right, is obtained by a very exquisite piece of equipment called the patch clamp. In our department, Dr. Amal Kanti Bera has this kind of equipment. So, which can be used to measure, to actually measure current through single channel. You see that there's a microelectrode, right, recording pipette is used to make a very tight contact with the part of the membrane which has some channels. Right, let us say that part of the membrane has only a single channel, very small part, like a few microns. Right, and that part you make a contact with this pipette and apply some suction. So that will suck up the membrane into it, and then you are able to isolate a single channel. And after that, the pipette itself acts like an electrode, and it can measure the currents, right, going through that channel. So for this work, Zachman and Neher got a Nobel Prize for physiology in 1976. Okay, uh, so we have this equation that x dot is equal to, or tau into x dot is equal to minus x plus x infinity. So now the question is, our original question is, we said that voltage controls GNA and GK. So now we are talking about channel closure and opening. Right now we need to figure out how the voltage controls the channel properties. So we need to now understand, because the GNA and GK, they depend upon the open close dynamics of the channels, right? Because if the GNA and GK are not constants, if the channels are open, then GNA and GK are high. If channels are closed, then they are low. And X determines the number of open channels. So therefore, the G's conductances depend on X's. X's in turn depend on these two quantities, tau and X infinity. So we need to figure out how the voltage controls this tau and so this problem of determining how voltage controls GN and GK now becomes the problem of determining how voltage controls X infinity and tau. So let us see that. So for that, so we see that we know that X infinity and tau come from, right, K plus and K minus. These are the ones that we just, right, put them in a different form to obtain X infinity and tau. So now the question is, how does the voltage control the rate constants? If you can understand that, everything else is just detail, right? So for that, let us invoke this Arrhenius expression, which you must have studied in your high school chemistry. That is, the rate constant of a chemical reaction is given by a formula like this, depends exponentially on the activation energy involved in that reaction, right, to make the transition from A to B. So here R is the ideal gas constant, T is absolute temperature. So in our case, the K minus and K plus rate constants are, so the activation energy actually depends upon the membrane voltage V, right? So therefore, the rate constants K plus and K minus are given by these two formulates, just similar to the same thing, but with a slightly different. Instead of activation energy, we're using voltage, because activation energy depends on voltage. So the first formula is K minus is equal to K naught minus times exponential minus beta V. Beta again is a constant. Similarly, K plus is equal to K naught plus times exponential of minus alpha V. So these two are K plus, K naught plus and K naught minus are constants, the independent of membrane voltage. The voltage dependence has now come through this expression. This is a key secret. So if you plug in these two expressions into these two formulae, right, 2 and 3, okay, so then you get these into these equations. x infinity is this, and tau is equal to this. Okay, so here again we define two new quantities, V naught and S naught. V naught is given by this ln of k naught minus by k naught plus by beta minus alpha. S naught is 1 by beta minus alpha. If we substitute for S naught and V naught in these equations, right, in these equations, you get a slightly different expression. Right. This can again be massaged into slightly different form. Okay, so let us look at, so basically what we have done is we've done a lot of algebra to figure out how the voltage, membrane voltage V controls x naught and x infinity and tau. Now let us see how these graphs change as a function of the voltage, because x infinity and tau is the one that controls x and x controls g. So therefore we need to see how the voltage controls x infinity and tau. So since x infinity is dependent on voltage in this form, or you can see this form also. So this function is what is called a logistic function. If you plot this, so 1 by 1 plus e power minus lambda x, let's take a general expression like this. So this function looks like this. Okay, on the negative infinity side, if lambda is positive, on negative infinity side it goes to 0, positive infinity side goes to 1, and at 0 it goes to 0.5. And the slope is controlled by lambda if lambda is positive. If lambda is negative, you just flip this curve and you draw it like this. So that's how it looks. And the same thing you can write in terms of tan h function, because you know tan h of x is given by e power x minus e power minus x by e power x plus e power minus x. Okay, so using that we are able to change this into this expression. Okay, so if you plot x infinity as a function of voltage, x infinity, right, it will look like this. It look like this what is called a sigmoid function, right? Where you see that, so it can have two shapes. One is starting from 0 at some value of voltage, it goes to a positive value, and then after that it goes to 1 with inside for at infinity. And this transition can be rapid or short, rapid or or long. And so the one where the case where it increases, right, with voltage, that happens when S naught is positive. Okay, and the case where it decreases, right, with increasing voltage, this happens when S naught is negative. So the reason we define this kind of a term called x naught is just to show this. That is, you can have two kinds of variation of x infinity as a function of voltage. One in which with increasing voltage the channels open, right? That is x increasing means what? X infinity increasing means that will cause x to increase, right? Because x simply follows x infinity, right? What does this equation tell us? X follows x infinity, right, with a delay of tau. That's what this equation is telling us, right? And that's what you see here. So if x infinity um, and in this equation, which is what we got when we solve it, right, it shows what will be x infinity for large voltage. So channels in which open with increasing voltage, they are called activation channels, right? So these are activation. The solid line indicates activation channels, and channels which decrease or close, right, with increasing voltage, they are called inactivation channels. So channels which are activated by increasing voltage, right, and channels which are inactivated by increasing voltage. The two kinds of channels, and that property or difference is captured by this parameter S naught. So similarly for inactivation channels, right, you have S naught is negatives, therefore the curve goes from a high value of 1 goes to 0 with increasing voltage. So like that, in terms of x infinity, there are two kinds, right, of channels, which are distinguished or differentiated by the parameter S naught. And one more thing you can notice here is the point where this transition occurs, that occurs at some voltage, right? That voltage is V naught. So we've defined two quantities here, S naught and V naught. V naught tells you at what point this transition occurs, at what point, at what voltage the channels change from closed state to open state or open state to closed state. The transition point is given by V naught, and whether the channels open with increasing voltage or close with increasing voltage, that is given by S naught. So this is the meaning of these two parameters. So let us look at time constant tau. Right? How does tau vary as a function of the membrane voltage? So here again, you just have, in case of tau, it is not like a sigmoid, it's more like a bell curve, right? And for a certain optimal voltage, the time constant is highest, and on both sides it goes down to zero, or it's very, very small. Okay, so now we need to go to kind of expand arguments a little bit more, right? It gets slightly more complicated. Until now, we talked about the channel dynamics as if the entire channel opens and closes, right? But in reality, what happens is the channel is a very complicated structure. It's actually a protein molecule, right? Not great at artwork, but imagine like a pore like this, right? Imagine a very long. So best example is take a Coke can and crush it a little bit, right? Imagine a very long Coke can where you can crush it at multiple points, right? For something to go through, right? The whole pore should be open. If you whether you crush it at one point or crush it at 3 points, it doesn't matter. Once you crush it somewhere, the pore is closed and nothing will go through, right? So just to capture the more complex nature of channel dynamics, people have invoked this kind of a more elaborate picture of channel closure and closing and opening, right? And for this, they introduce a new concept called gates or channel gates. That is, in a given channel, the opening and closing is controlled not by overall closure of channel, overall opening of the channel, but he says these people say that this is Hodgkin Huxley's original description. They say that there are multiple gates inside the channel, and even if one of these gates close, right, the whole channel closes. You can have so here all gates are open in the first picture on the left side. On the right side, you see all gates are closed. These gates are a bit of a fiction because there's no such thing as there's not like a trap door where right, it opens and closes. Basically, it's a very complicated protein molecule, right, where it can have lots of different uh, you know shape changes all along the pore of the channel, right? And to indicate that the dynamics is so complicated that at different parts of the protein, different things happen. So to indicate that, they've invoked this kind of a fiction called a gate. And so they talk, now that we talk about the opening closing of gates and not as a channel. Or we'll relate the opening close dynamics of the single gates to the opening close dynamics of the entire channel. Okay, so whatever we described until now as open close dynamics of whole channel, we now applied it to a single gate. And in terms of the open close dynamics of the gate, we'll try to construct the open close dynamics of the entire channel. So this is the next step, which is slightly subtle, but let me know if you have any doubts. So the x variable which we defined until now, which indicates the number of fraction of open channels, we now use it to denote the fraction of open gates. Right? Actually, we use the term probability. We use the open probabilities of the gates. So let us say there are k gates in a given channel. X1 denotes open probability of gate 1, X2 denotes open probability of gate 2, and Xk for gate k, and so on. So since we have now switched to probability perspective, right, if X's are the probabilities of single gates, the probability of the whole channel to open is simply so let, because even if one gate is closed, the entire channel is closed. That's the kind of relationship we have between the gate closure and the channel closure. And that's how the story is, is made up of. So the probability of opening of the entire channel is nothing but the probabilities of opening of all the gates, right? So x1 times x2 times x3 times xk. Because the channel is open only when all the gates are open. So now with this picture, we are now ready to write down the equations for the channel dynamics of both sodium and potassium. So like I said, a given channel can have multiple gates, right? Now, what kind of gates does a sodium channel have? And so whatever we described before as dynamics of the whole channel, we are now applying to the dynamics of single gates. That's what I said a moment ago. So let us do that. So for the sodium gates, right, you have, for the sodium channel, you have 4 gates. It turns out there are 4 gates. 3 of them are activation gates, 1 is an inactivation gate. What does that mean? So we talked about activation channel as one which opens with increasing voltage. Right, inactivation channel is one which closes with increasing voltage. Now we are applying the same concept to the single gate, and now we say that an activation gate is one which opens with increasing voltage. Inactivation gate is one which closes with increasing voltage. Right. So when you have 4 gates in the same channel, 3 of them are activation, 1 of them is inactivation. It's like within the channel, different gates behave differently to voltage, and there's some internal conflict, you can say. Right, these 3 gates tend to open with increasing voltage. This gate tends to close with increasing voltage. So there is some internal conflict, right? And now we write down the. Earlier we wrote channel dynamics. Now we talk about gate dynamics. Or more standard jargon that is used is gate kinetics. Right, gate kinetics is very similar to what we have written. Right, originally we wrote this. Right, x dot is equal to minus k minus x plus 1 minus x times k plus all that, right? Now this we originally wrote for x, which is the fraction of open channels. Now we are writing it to single gates, right? And we are describing using this equation the probability of open gates. Therefore, m is called the gating variable. Each gate has a gating variable. And in case of sodium, there are 3 activation gates and 1 inactivation gate. Okay, so M denotes like it's like a common variable for all the activation gates of sodium, and H is like a common variable. Sorry, there is only one. There's only one inactivation gate. So H denotes that gate, the gating variable for that gate. So this is the gating variable for activation gates. H is gating variable for inactivation gate. There's only one gate. So we need to find out these functions. Just as k plus and k minus are functions of Vm, here alpha, we use the notation alphas and betas. For M, you have 2 functions alpha m and beta m. For H, you have 2 functions alpha h and beta h. They are all functions of voltage. Similarly, for potassium, there are again 4 gates. In this case, life is much simpler. There are just 4 activation gates, all 4 activation gates, and the gating variable for them is n, right? And that's given by this equation. dn by dt is equal to alpha n into blah blah etc. etc. And now, so there are 4 gating variables, 3 m's and 1 h, right? Like I said, the probability of gate opening is the product of all the gating variables, that is which denote the gate open probability. So therefore, since there are 4 gates, the first 3 gates have variables m, same m, because they're identical gates, so m, m, m. And the 4th gate is an activation gate, which has a gating variable of h. So therefore, the gate open probability for the sodium channels, channel open probability for sodium channels is m times m times m times h. Therefore, it's m cube times h. if GNA max is the maximum conductance that the channel can take, right, then that means this will happen when all the sodium channels are open. So therefore, when some of the sodium channels are closed, right, and only a fraction of them are open, the actual conductance GNA becomes GNA max times m cube h, because m cube h is a probability of open sodium channels. Okay, so that is how you calculate the sodium conductance. Similarly, for the potassium conductance, GK max is a maximum conductance of potassium, which means this is the conductance when all the potassium channels are open. But n is open probability of single gate, and n power 4 is open probability of the whole channel, right? So therefore, the conductance of potassium is given by GK max times n power 4. If you plug this into the final circuit, right, you have all these dependencies. So the current is given, total current is given by this, which is this first expression. Now GNA and GK, originally we just said that they are functions of voltage, but we didn't indicate how they are functions of voltage. So now we are saying that GNA now becomes GNA max times m cube h, GK becomes GK max times n power 4, right? So these two expressions. And m and h and n, the three gating variables, are given by these three equations. So it's a pretty complicated model. It is governed by three differential equations. So this is 1, 2, so I'll call this 2.1, 2.2, and 2.3. So totally 4 differential equations, but highly nonlinear differential equations. And the alpha and beta functions, there are 2 functions for every gating variable, are given by these expressions. I mean, don't worry about, you don't have to memorize this or anything. So if you, to summarize, to look at all the different dependencies of various variables, VM controls, actually VM controls alpha beta functions, right, by this formula, right, VM controls alpha and beta functions. And alpha and beta functions determine m, h, and n. So you need to actually put alpha beta functions, right, and then these in turn control m, h, and n. M and h together control GNA, and n controls GK. Now GK and GNA show up again in this equation, equation number 1, right, and this and through that equation, GK and GNA control VM, right? Therefore the loop closes. External input, operates externally on this loop. So VM controls alpha beta controls MHNs, MHNs control GNA GK, GNA GK again control VM, and the loop goes on. So it might look very complicated, but what is interesting, it shows such rich behavior, right, as we will see in the next class with some simulation demonstrations. So what happens is, as you vary this input current, right, inject a DC current, a constant current, and see how VM varies with time. When you give a small current, VM increases a little bit and comes back to the baseline value of minus 70 millivolts. And M and H also just show small blips, and otherwise after that they again settle down. But when you increase your input current and make it go beyond the threshold value, suddenly you see this sharp spike occurring in the voltage, right? And as you increase input current further, these spikes, instead of a single spike, you will see a whole series of spikes. And as you go further, this series increase in frequency, and as you increase further, right, as you increase current further, the spike frequency increases. As you increase it further beyond a point, the spike's amplitude goes down, and it stops looking like a spike. Right? It looks like a small ripple. So beyond that point, you say that there are no action potentials. So these equations are okay, the 4 equations, but they show very rich behavior. Right? We will see all this in more detail in the next class. Then we'll give you an assignment based on the Hodgkin Huxley model. Right? I am sure it's might seem a little complicated, but let me know if you have any questions. Then I'm happy to repeat some of these key points in the next class, and clarify any doubts on the model. Any questions?
Sir, I have a doubt.
Yeah, yeah,
So initially we discussed the dynamics of a population of channels, and then we went on to single channel dynamics, right?
no, no, sorry. Initially, I discussed dynamics of population of channels, and we wrote down all these equations. Right? Sorry, this um, all this stuff, right?
Yeah.
Up to here, we said this is all about gate. This is all about um, yeah. So we discussed this all about channels, but after some time, I said so. I switched to a more complicated model of a single channel, where within a channel there are multiple gates, right? So using just a single variable x, I won't be able to describe the open closure of a channel. I need to look at a more complicated model of a channel, right? Where there are multiple gates within a channel. Now, how do I describe that? What we have done is we've just moved all these equations where earlier they were applied to a whole channel. Now we are applying it to single gates within a channel. And by invoking this principle, that the whole channel is open only when all the gates inside the channel are open. And now I'm interpreting the gate variable x as not as a fraction of gates open, but the probability of gate open, which is a similar notion, right? So then
So
I
the
get the open probability of the channel. So thing is, here also I'm looking at a population of channels because I'm only talking about probability of opening of a channel, right? Yeah.
but
What is the question?
here we considered the probabilities of opening and closing of single gates, so that can be done only for
Yeah.
one particular channel, right?
Yeah.
Uh,
But one per channel, but we are only talking about probabilities, right?
okay. Okay, then
This is
are
not
we
a
gonna
we apply this to a population of channels now.
the second part also?
Yeah,
Where
second part also, because the single gate dynamics, single channel dynamics is very complicated. We saw that it's very binary.
okay.
Those smooth variations of conductances you get only when you take a population,
Okay.
right? So this probability that we now derive earlier, say it's a simple dynamics, x dot is equal to minus x plus x infinity. Whereas now that x is now replaced by is now elaborated into many variables. Right, gate dynamics is not one variable now. It's governed by many variables. As many variables as there are gates inside a channel. Right, so we have done that, and we said for sodium there are 4 gates, and then each of the gates has a variable, and then we said the channel open probability is now m cube times h, not just x. Right, it's m cube times h. It's a product of 4 variables. Okay. Uh, Using and so this is all probability, so which is meaningful only when you take a population of channels here also.
So
So
these
to
are the
summarize, yeah, go ahead.
equations for all sodium channels, like all sodium
Yeah,
channels you are
yeah,
describing using.
yeah. So GNA is the conductance of a whole population of sodium channels. This is not for single channel. Single channel dynamics is very complicated. You need a very different kind of a model for that. Right. Only thing is we derive this GNA from by invoking this other concept called gate, and we write the gate dynamics. So I could have described the more detailed picture right away, right from the beginning, but I thought that would be too complicated. I said, let me first tell the story as though the channel is a single unitary entity and write down the equations. Then I'll say that that's not sufficient because Hodgkin Huxley have resorted to a much more complicated channel model. And then I just moved the concepts which were originally applied to a whole channel, and I applied them to a single gate. And from gate, I constructed the dynamics of the entire channel. right? I just did it in 2 stages so that it won't look too complicated. But please let me know if something is not clear, I can clarify. But it's a good question, good that you asked it. Because the transition is where people get, find it a bit confusing.
I had another doubt.
Yeah,
Are all voltage independent channels considered leakage channels? I mean, they have other types of gating, right? You can't,
yeah. So in this model, we are only interested in voltage gating or no voltage gating. We're not considering any other property at all. This model of this objective of the model is very simple. If I inject current into the cell membrane, what is the response of the cell membrane voltage? Right.
Okay.
So other things like for example, ligand gating shows up in neurotransmission. We'll discuss that separately in a separate model later on in the course. And phosphorylation gating we don't even discuss in this course. Switch gating also we don't discuss in this course. So we are looking at one kind of gating in one context and writing down the equations for that.
So, are all channels which are not voltage dependent leakage channels? Or
In this context, because we are not considering
okay,
anything else. That's why in
okay,
this context, that is the language used.
okay.
All right. And
Thank you
there
so
are
much.
some channels which are dual gated. They can be
Yeah.
controlled by both ligand and voltage. And they have a major role in some of the memory properties of the brain. Right. So synaptic plasticity, by which information encoded in synapse, this kind of dual gate channels play a major role. Right. All that we'll see later, much later in the course. In this
Thank you.
context, this is the terminology. Okay, any other questions? I mean, if you ask questions, it will be more interesting because I also can, I'll get better clarity when I try to answer your questions.